Now the other thing, what are these oxidation states used for? They're used as a bookkeeping method to recognize if oxidations and reductions are taking place. So just a couple of examples here. Let's take the combustion of propane. Now, a combustion reaction like this is where a hydrocarbon reacts with oxygen and we get carbon dioxide and water. Now, you may not know this, but combustion reactions are always going to be oxidation reduction reactions. And you can sort of tell if you focus on oxygen, it's got a 0 as an element for an oxidation state, and now it's part of compounds where it's usually -2, right? So oxygen in this case goes from 0 to -2 during the reaction. So we've had a change in oxidation state, change in oxidation number. So the oxidation number is decreasing. So what has happened to the oxygen? Has it been oxidized or reduced? Well, we say it's being reduced. So using oxidation numbers, we recognize reduction is when there's a decrease in oxidation state. A definition with a better physical meaning would be that oxygen has gained electrons. Now, has it gained them to become an ion? No, but it's by combining with other elements and having a greater electronegativity, it has gained electron density by being able to pull electrons away from those elements and take on a slightly negative charge. The hydrogen, what's happening to hydrogen? Is that being oxidized or reduced? Well, on the left, it's in a compound, it's +1, and same on the right. We're really not changing anything. So hydrogen is not undergoing oxidation or reduction. Carbon, on the other hand, is going, we already calculated this before. Carbon in propane, the average oxidation number is -8/3. And notice it's negative because it's bonded to hydrogen, which is less electronegative. Carbon's more electronegative than hydrogen. But in the product, carbon is bonded to what? Oxygen. And oxygen's more electronegative. Electrons are now being pulled away from the carbon, so it's got a positive oxidation number. So the oxidation state of carbon has increased. And what would that mean? What would that imply? If you increase the oxidation number, it means it's being oxidized. A more physical, meaning with a more physically meaningful definition would be that carbon is losing electrons or losing electron density in this reaction. Just a couple of other observations. Oxygen is being reduced. But what else do we say about oxygen? What kind of an agent is it? Do you remember that from Gen Chem 1? It is an oxidizing agent. So oxygen itself is being reduced, but we say it's the oxidizing agent. Why do we say that? Because it's oxidizing carbon. You see, what is happening to carbon? It's being oxidized. It's losing electrons or losing electron density. What's it losing it to? It's losing it to oxygen. Oxygen's taking away the electrons or the electron density. So oxygen is responsible for oxidizing carbon. So it's therefore the oxidizing agent. And remember, just an easy way to kind of remember this until you become more familiar with it is whatever is happening to oxygen, it's being reduced, it's the opposite kind of agent. So oxygen itself is being reduced, it's therefore the oxidizing agent. And you see, by being an oxidizing agent, it's taking electrons away from carbon. By gaining those electrons, it's itself being reduced by gaining those electrons. So just the opposite for carbon. Carbon is being oxidized, so it is the reducing agent, the opposite agent, right? And why is it the reducing agent? Because it is putting electrons onto oxygen. It is reducing the oxygen. By being oxidized itself, it's losing electrons to the oxygen and reducing the oxygen. Now, hydrogen, you might say there's nothing to say here, but just a quick reminder. We just looked at carbon and oxygen and talked about the difference in electronegativity and why carbon is being oxidized. When it goes from being bonded to hydrogen to oxygen, carbon is being oxidized. So, why is hydrogen the same oxidation state? You might say, well, if oxygen's more electronegative than carbon, look at propane, right? Hydrogen's bonded to carbon here. And carbon's more electronegative, and so it's pulling electrons away. But in water, hydrogen's bonded to oxygen, and oxygen's pulling electrons away even more strongly. So wouldn't you think of that as hydrogen's being oxidized? It's losing even more electron density? The answer is no. This is just a method of bookkeeping to tell us what's oxidized, what's reduced. Okay, it's not the oxidation state is not quantitatively meaningful, but it allows us to recognize oxidation and reduction. So when you see hydrogen here, each hydrogen is bonded through one bond to carbon, and it's giving up each one is giving up electron density to the carbon it's bonded to. It's still bonded to a more electronegative element, oxygen, in the product, and giving up electron density through one bond. Each one of those hydrogen atoms is. Oh, this isn't balanced. I apologize. I lost my numbers here. This reaction should be balanced. We should have a 3 here and a 4, and we should have a number in front of oxygen. So I do apologize for that. But anyway, the hydrogen, the situation's not changing. In both the reactant and the product, each hydrogen atom is bonded to one other atom, which is more electronegative. Now, for the carbon and the oxygen, the atoms they're bonded to are changing. Sometimes it's also the change in the number of bonds from the atom to, maybe it's bonded to the same number of electronegative atoms, but maybe it's a double bond instead of a single bond. So there's different reasons why you might see a change in oxidation state. But it's like I said, it's very non-quantitative. It's not meaningful, like what these numbers want, +1, +2, what they really mean. It's just a bookkeeping method to help us recognize oxidation reduction. Okay, now, I lost my... No, this one's balanced. Okay, so this one's balanced, but the previous one I lost my numbers somehow. But this one we're okay. So let's do another one quickly here. This is a single replacement reaction. And do you remember in Gen Chem, those types of classifications, double replacement, single replacement, decomposition, etc. So, a thing to note here, all single replacement reactions are oxidation reduction reactions. If you look at it, here's a single replacement reaction. Take magnesium. It's going to be 0 by itself. Now it's in a compound. Copper's in a compound. Now it's by itself. It's going to be 0. So you're automatically going to have an oxidation reduction with one of these reactions. Now the reverse is not true. Every oxidation reduction reaction is not a single replacement. There are many different types of oxidation reduction reactions. So, okay, let's take a look at copper for instance. What's copper doing? It's going from +2 to 0. So it is a decrease in oxidation state. It's being reduced. And magnesium, what's happening to that? 0 to +2. It's an increase in oxidation state. It's being oxidized. And chlorine is -1. Nothing's happening. It's just a spectator ion in this reaction. All right. Last thing on these slides, oxidizing agent and reducing agent. Which is the oxidizing agent? Well, it's the one being reduced. So copper is the oxidizing reagent. It's oxidizing magnesium. And magnesium is being oxidized by reducing copper. So it's the reducing agent.